for invitation. It's a big pleasure for me to stay here in Brazil. Yeah, I love this country. I love food, weather, people here. So I know Pavel for about 20 years, I think. Yeah, we met for the first time in Düsseldorf, where we're both visiting Fritz Grunewald. And after that, we started to work on cohomological goodness in Bianchi groups and then in arithmetic linear groups. So, and I'm very grateful to him to introduce me to that subject, the subject of three manifolds groups. Pavel is a very known specialist in profinite group theory, but I also appreciate very much his papers which relate profinite groups with residually finite groups. And this talk will be of this kind. So I will speak about profinite rigidity. First, I will introduce somehow general notion profinite rigidity and explain some general results about profinite rigidity. And in the second half of my talk, I will concentrate on the profinite rigidity of free and surface groups. So in this talk, C will be a pseudo-variety of finite groups. By pseudo-variety, I mean a class of groups closed under subgroups, quotients, and finite direct products. So we mostly will work with the class of all finite groups, but sometimes I also will consider the class of all finite soluble groups, or class of all nilpotent, finite nilpotent groups, or also class of all finite P groups. So in this talk, the group gamma, which I consider, all groups that I will consider will be finitely generated groups. So take a group gamma, which is residually C. So residually C means that for any non-trivial element in gamma, there exists a normal subgroup in gamma such that the quotient is in C, but G is not in C. So this is residually C group. And for residually C group, we can define the notion of C genus of gamma, which we will always denote in this way. And this is the class of groups consisting of finitely generated groups, which are first residually C, and the second, G has the same quotients in the class C as the group gamma. So this notion of, its variation was introduced by Fritz Grunewald and Pavel in around 2000 something, and was published in 2011. So there is another way to introduce C genus. So if we have finitely generated residually group C, finitely generated residually C group G, so G belongs to C genus of gamma if and only if the C completion, pro-C completion of G is the same as pro-C completion of gamma. So I will use this kind of this characterization very often in this talk. So pro-C completion, so again, this is inverse limit. We take all quotients which are in C, and we take the inverse limit. So one remark that I want to say is that, of course, if we have two classes of groups, C1 and C2, and gamma is residually C1, of course, it will be also residually C2, So we can speak about C2 genus is C1 genus. So it's not always true that C2 genus, it belongs to C1. So this is because it's not automatically that any group here is residually C1. No? So we will see this kind of examples. So the general question in this subject is the following question. So we have a pseudo variety of finite group C. We have a residually C group gamma. And we want to know what properties of gamma do inherit the groups from its genus, C genus. And of course, the most satisfactory answer on this question is just say that gamma is any group from C genus of gamma is isomorphic to gamma. So in this case, we will say that the group is prosi-rigid. So. Yeah. So in the case, okay, the most interesting case when the class of groups consists of all finite groups, we simply say that gamma is profinitely rigid if its finite genus consists only of gamma. Sometimes it's also called absolutely profinitely rigid. Because sometimes we can consider this, consider groups from some class of groups. Yeah, so let's say we can consider three manifolds groups and compare profinite completions of three manifolds groups. In this case, we will say that it's profinitely rigid in some class X of groups. Okay, let's see examples. So, okay, of course we will start with, okay, probably I have to start with zero example, it's finite groups. Of course, finite groups are profinitely rigid, it's clear. The first non-trivial example consists from finitely generated abelian groups. So also it's not very difficult to see that they are profinitely rigid, and in fact they are pro-nilpotent rigid or pro-soluble rigid, because they are nilpotent and the profinite completion is nilpotent and pro-soluble and soluble. But you can see that already virtually cyclic group is not always profinitely rigid. So this is an example of virtually cyclic group, which we construct as a semi-direct product. So we have two groups constructed in similar way. We take a semi-direct product, Z acts on C11, on the cyclic group of 11 elements. And okay, it's not difficult to see that the profinite completions are isomorphic, but the groups are not. So this is. Okay, if we consider nilpotent groups, so free nilpotent groups of class C, so if we fix class C, they are profinitely rigid. So one can show. However, there are finitely generated nilpotent groups which are not profinitely rigid. Yeah, if we extend a bit a class of groups and look in virtually polycyclic groups, so here we have a result of Grunewald and Siegel. So it's the end of a series of results, but this is somehow they closed this problem. They showed that these groups are almost profinitely rigid, which means that their profinite genus is finite, is always finite. So for this group. But they are not always profinitely rigid, absolutely, no? Because we have this example. And also if we go to bit further, we consider metabelian groups. So there is example due to Pickel, who showed that there is a finitely generated metabelian group such that its genus, its profinite genus is infinite. So you see that it's, okay, there is no order in this picture. So it's like we have very different examples, different properties. But all these examples have something in common. This is examples, the group satisfying word identity. And so we can ask, what about groups which contains a non-abelian free group? So such group is called full-sized group. So I will refer to this group as full-sized. Okay. So in this case, we can construct a lot of examples of groups which are not profinitely rigid, and you see that you will see the relation with other part of group theory or algebraic geometry. So the first example comes from algebraic geometry. So consider an algebraic variety. So what I mean by algebraic variety, I mean smooth, irreducible, quasi-variety, quasi-projective variety. Quasi-projective. Yeah, so if we consider such algebraic variety and look at its C points, of course, it's a connected topological space, and we can consider its topological fundamental group, which will denote by P1x, and also can consider profinite completion of its topological group, which is known as the étale fundamental group of this variety. Now we can take an automorphism of complex numbers and apply this automorphism to the coefficients of the polynomials which defines x. So we will obtain another set of polynomials which will give us another algebraic variety, which will be also smooth, irreducible, quasi-projective. And now what we know, so this is quite standard results, that the étale fundamental groups are isomorphic. In particular, we will have the isomorphism. So we will have the isomorphism of the profinite completion of the fundamental groups of X and X sigma. Okay, it was Serre in 1964 who constructed the first example where in fact the groups, fundamental groups, are not isomorphic. So now we have a lot of examples of this kind. For example, there are many papers concerning so-called Beverly surfaces. So it's, okay, I put now few names, but there are much more. So there are surfaces, that they have surfaces, something of this kind, some finite group satisfying some list of conditions, and for these surfaces, one can produce a lot of examples where you don't have isomorphism of the fundamental group of X and X sigma. Also, there are examples in more sophisticated algebraic varieties as Shimura varieties. So this is one way to construct examples, and all these groups contains free groups, so they are all full-sized groups. Another very popular way to construct full-sized non-profinitely rigid groups comes from arithmetic groups. So for example, this is probably the most easiest way to describe it. So take two number fields, K1 and K2, which has isomorphic profinite completion of the rings of integers. So it's this is called adelic equivalent. So there are examples of fields which are adelic equivalent. And now consider gamma I, which is SI3 over the rings of integers of these fields. And so because of congruent subgroup property and because this property of adelic equivalence, we obtain that the profinite completion are isomorphic, but okay, it's also easy to see that the groups are in fact not isomorphic. And okay, there are also many examples of this kind. I just want to cite part of abstract of the recent paper of Becher. So basically, he proves that typically high-rank arithmetic lattices, so when you take one, there exists a finite index non-isomorphic subgroups, they have isomorphic profinite completion. So you have a lot of examples, of course, in this way. Also, we can construct examples using our previous example here. Here, when we construct virtually cyclic, doing the same, so consider the same strategy, we can construct virtually free examples, which are full-sized. Yeah, and in fact, until very recently, it was not known any group which is profinitely rigid, full-sized, and it was 5 years ago when Brights and Mark-Reynolds, Reit and Splitter, they constructed first examples. So the first examples was Kleinian groups, and the second paper, they constructed many examples of function groups. So, okay, one of the Kleinian groups, which is profinitely rigid, can be, okay, Bianchi group, in this case, Bianchi group, which profinitely rigid can be constructed in the following way. We take a primitive root, cubic root of unity, we consider PCL2 over Z, adding this root of unity. And there are many examples of triangle groups now. I took one of them. For example, this triangle group is profinitely rigid. So in fact, okay, this groups is virtually surface. Yeah, this group is virtually surface. But for example, we don't know yet any example of virtually free group which is profinitely rigid. Okay, so yes, if we consider full-sized group, of course, the most natural question is what about free and surface groups? Yeah. Okay. So, any questions so far? Because I will pass to my second part. Yeah. So when I say free group, of course, I always mean non-abelian free group. And when I say surface group, I always mean hyperbolic surface group, which, okay, we have two families. So the fundamental groups of compact closed surfaces of negative Euler characteristic. So this is a presentation in oriented case, and this is non-oriented case. Okay. So first observe that gamma is residually nilpotent, so we can gamma, so now gamma is or non-abelian free group or hyperbolic surface group. So in both cases it's residually nilpotent, so we can first consider nilpotent genus of gamma, and this is a very known subject. So when gamma is free, the groups from the its nilpotent genus called para-free, and when it's surface, they called parasurface. So para-free groups were studied a lot by Baumschlag and others, and you can construct infinitely many examples of para-free groups, and in this case, the genus is infinite. So I want to mention a conjecture of Wilton. I will somehow use it later. So there is a conjecture that finitely generated para-free groups are hyperbolic and virtually compact special. So by hyperbolic, I mean word hyperbolic in sense of Gromov, and virtually compact special, so I will not define it, but okay, some indication. So it was introduced by Haglund and Weiss 15 years ago. So they introduced some special cube complexes, and compact special groups are the fundamental groups of this of compact special cube complexes. So the examples, the main examples are racks. So in the previous talk, I think, in previous talk we defined it. They were defined it, I repeat. So you have a graph, finite graph, and you generate the group by vertices, and the relations are commutators if these two vertices are connected in this graph. So compact special groups can be embedded in racks, and in fact can be embedded in a very nice way. They are virtually retract. So there is such embedding in some subgroup of finite index, such that our compact special group is retract of this subgroup of finite index. Okay, so now consider the prosoluble and profinite genus of gamma, and here we have the following conjecture, that in this case we believe that gamma is pro-S, a pro-F, profinite rigid, prosoluble, a profinite rigid. So in the case of gamma is free, entonces, and when we speak about profinite completion, in this case it's known as Remesninnikov conjecture. Okay, now I list some results which are known about these groups. Yes. In the conjecture of Wilton, gamma is para-free.
But in your conjecture, gamma is only free surface? Because gamma is pro-free and pro-free.
Yes. Yes. Yeah, okay, you can make the same conjecture also para surface, because, yeah. So, really, para-free case were studied more than para-surface. So what we know about F genus of free and surface group, or prosoluble genus of free and surface groups. So the first result that I want to mention is that they are residually P. So for free case, I obtained it in 2021, and for surface case in 2022. It's not published yet. But in particular, what we have, the following inclusions. So, okay, so what we hope that this is only gamma. Also, we hope that this is only gamma. We know that this inclusion is strict. As I said, there are a lot of groups here. And in fact, I realized, preparing my talk, that I don't know nothing about this inclusion. It was not studied. Maybe I missed something, but it's also interesting to understand what is this difference. Maybe it's equality. The second result that I want to mention is the structure of two generated subgroups, or free groups, two generated subgroups of G. So it appears in the result of Baumschlag para free groups already, and in recent preprint of Morales, that all two generated subgroups of a group from genus S genus NP, in fact NP genus of gamma is free. And another result, which is due to Wilton and Morales, is the following. If we consider the following class of groups, so we start with free groups and then construct amalgamated products and I-chain extension with cyclic H groups. So this class X. So there is only one. So the intersection of F genus of gamma with X is gamma. So in this case, we know, at least for profinite genus, the answer on this conjecture. So this result basically is due to Wilton, who proved it assuming that groups are hyperbolic, and Morales realized that it's not necessary to assume hyperbolicity. It follows from the assumption that G is in profinite genus of gamma. Yeah, so you see that we not know much about pro S and pro F genus of free and surface groups. But still, I want to propose a program to solve this conjecture, and I will comment on this program. So what I propose is that it's of course, as you see, it's related with conjecture of Wilton, show that G is virtually compact special, show that G is hyperbolic, and using our knowledge about these groups, prove that in this class of groups, there is only one group in this genus. So what I can say, I really believe that this one is possible. Yeah, it's really so somehow the result of Wilton that I mentioned before provides strong evidence that one can extend these techniques to more general class of groups, in particular to this class of groups. But this too is impossible at this moment. Basically, the problem is that we don't know. So in order to do such things, we need a good action of G on some good space, and we don't have any hint about what kind of space it is. But still, what I can expect that we can, instead of proving these two steps, we can prove some consequences of them, some algebraic consequences, and use these algebraic consequences, corollaries, in order to settle this conjecture. So I want to explain why I think it's possible, or at least one can believe that it's possible. Yeah. So one of the most important results in three-manifold theory after the solution of Poincare conjecture or Thurston conjecture is virtually a solution of virtually Haken conjecture. So virtually Haken conjecture says the following: we start from hyperbolic closed three-manifold, and it says that there is a finite cover that has a very nice structure, and this finite cover fibers over the cycle. So it's a fibration. So in terms of group theory, you can formulate it the following way. We start with the group G, which is the fundamental group of this manifold. Then we can find a subgroup of finite index, which is a fundamental group of this cover, and the group H is fibers. Means that there exists splitting of H as semi-direct product, where this group is finitely generated. So this what I will. So this what I will say that if we have such situation for G, I will say that it's virtually fibers. So the solution was obtained by Agol, and it consists basically from two steps. So the first step is to show that the fundamental group, is virtually compact special, but it means that, as I said, it's virtually RAG, virtually subgroup of RAG. Yeah. So this is what I defined before. Yeah, here. So that compact special groups can be embedded in this kind of groups, which we understand well. And what we really need, it's not that it's virtually RAG, it's virtually reverse. I will define it later. And the second step was to show that if P1M is virtually reverse, then it is virtually fibered. Okay, so this was his strategy. So, okay, this part of proof is really very deep combination of ideas from three-manifold theory and geometric group theory, but the conclusion is completely algebraic. And the good point that we know this conclusion in our case. In our case, we have reverse. And reverse comes from this result that I mentioned here, this result that the groups are residually P. So if they are residually P, so we of course understand their Pro-P completion, and from this we easily obtain that they are reverse. And now in the second step in this proof, it's again, Agol's proof used a lot of three-manifold theory, for example, Thurston norm. But now we have another alternative proof for this step, Dukilak. And this is pure algebraic proof. So the result of Killock is the following. If G is reverse, and the first L2 Bethe number of G is 0, then G is virtually fibered. You see, here you don't have any mention of three manifold groups. It's general algebraic result. Okay, so yeah, few words about proof of Killock, because I will use this paper later. So in the case of reversals, L2 Bethe numbers can be defined in pure algebraic way. So in this case, you can embed the group ring to some division ring, and then calculate this L2 Bethe number as dimension of this division ring of this Tor functor. So it's pure algebraic invariant. So if you want to define L2 Bethe numbers for arbitrary group, it passes through analysis, considering von Neumann algebras. But in this particular situation of reversals, it's you can do it in pure algebraic language, defining some nice, very nice skew field division algebra D. And what Killock did, it's really his main contribution, how it's to show, so he found a new description of this division ring. Yeah. So you see that, okay, I think that this one is very difficult, but at least if we can obtain some algebraic consequences without showing both things, maybe we can attack the general conjecture. And okay, I will show now some example of how reversals can be used in order to prove some variation of this conjecture. Okay, now I will define what is reverse, because so what is reverse? It means the following. We say that the group is reverse if exists a finite index normal chain of finite index normal subgroups of G, such that they have trivial intersection, and we have the following situation. So we have that this for each hi and hi plus 1, there is another ki plus 1, such that this quotient is torsion-free abelian. We also can speak about serial affairs if these groups are in the class C. So as I said before, so we have the following result, that if we have a group G from profinite or prosoluble genus of gamma, then this group is NP reverse. Yeah. So how can we use this property? So if you consider free group, so free group has the following nice property. If we have any non-trivial finitely presented model of a ZF has a non-trivial finite quotient. Okay, you can imagine that such kind of results, if you have such kind of results, it can help you a lot in order to prove profinite things related with profinite rigidity. So this first result, it's a bit technical, but it's of this kind. So we have a reverse group G. We have a finitely generated ZG model L, which is free. And we want to analyze this quotient, basically. And assume that this quotient does not have finite quotients. Yeah. And we have these two conditions, two technical conditions. So in this situation, what we can show that this quotient is 0. So we have this, if this quotient is infinite, basically, yeah, it's probably better to formulate for us in the following way. If this quotient is not trivial, so if we forget about 1, if this one is not trivial, so it has finite quotients. Yeah, and the crucial part of the proof is this description of this division ring, which was done by Killock in order to substitute this second part of the proof of Agol by more algebraic argument. And this is also very crucial in the proof of this theorem. Okay. Yeah, so I have time to give one proof. Yeah, maybe. Yeah, so let's now formulate a problem, which it's some variation of a problem about profinite rigidity. So this problem was suggested by Grothendieck. It comes also from algebraic geometry, but I formulate it in pure group theoretical way. So assume we have a group gamma, which is a residually finite group, and assume I take some embedding of some subgroup. So we call this pair Grothendieck pair if the induced, so of course you have embedding, it induced an homomorphism of profinite completion. So we say that this is a Grothendieck pair if induced homomorphism is isomorphism, but U is not. Okay, U is not means that P is not gamma. No? It's proper subgroup of gamma. Yeah, basically. So Grothendieck asked whether there are Grothendieck pairs, of course he did not call them Grothendieck pairs, of finitely represented groups. And it was a hot topic, and finally the solution was done by Breitzen and Grunewald in 2004, at the beginning of this century. The answer is yes. So my theorem is somehow mix between Grothendieck question and the question about profinite rigidity. So I consider the following situation. Take a group gamma, residually finite group, and assume it has a subgroup F, which is free. And assume that this embedding induced the isomorphism of profinite completion. In particular, this means that gamma is in a profinite genus of F. No? So the theorem says that, in fact, it only can occur when gamma is free group. Okay, the proof is the following. We start with the left ideal of Z gamma, which is the augmentation ideal, M. Now we have free generators of our group F, subgroup F, and we associate to it the following model L. And this model is free, okay, because the group is free. These are free generated of this group. This module is free. And now we want to use theorem B. So we check these conditions. L is free submodule. Gamma is Röfers. This is because of this. Yeah, and these groups are Röfers. ML, this quotient does not have finite quotients. This is exactly because of this condition. So because of profinite completion induced isomorphism. Okay, this is I did not define free, but basically, okay, this is because it's embedded in Z gamma. It's embedded here. It's automatic that it satisfies this condition. This condition is slightly more difficult to prove, but okay, you check it, and finally, theorem B gives you that M is L. But this is, if you now translate it, it means that the homomorphism is isomorphism. And the proof is done. Okay, I have another application. So this is now about surface group. So this is a joint work with Ismael Morales. We have a more general result, but okay, for simplicity, I will state it in this form. So in this case, we can show that if you take a residually finite one-related group, so this is in the class of one-related group, and the profinite completion of this group is isomorphic to profinite completion of some surface group, then in this case, you obtain the isomorphic. Yeah. Okay, interesting observation that we don't know how to prove this for free group. So in this case, surface groups is easy. In fact, I believe that in this conjecture, really I believe that surface case it's easy. Surface group has some structure, at least some structure, and free group it's a very difficult object in this case. Okay, I will not explain the proof. If you want, you can ask, but yeah, I will finish here. Happy birthday, Pavel.
Does it make sense to consider something like virtual rigidity, such that to ask whether if rigidity does not hold, but nonetheless there are finitely many groups which have the same completion?
Yeah, okay, I called it almost rigidity, no? It's a result of, when I explained the result of Grunewald and Siegel, it's exact, no? It's, yes. Almost, yeah, of course, it's also a very interesting question. Yeah.
Mm-hmm. More other questions?
So do we know finiteness of the genus for freer surface groups among some class? For instance, I don't know, hyperbolic or something, is this known?
In some class, what class? Yeah, okay. So, for example, one-related groups, for surface groups, there is only one. But, where, yeah, I don't know. It's in some classes finite, but not know whether it's one. No, this is your question. No, I don't know such class. No.
Okay, thanks.
More questions?
Thank you for a very interesting talk, first. I actually have two questions, but maybe I don't know how. First, answering. There is another, what Enrique asked also. You already mentioned the result of Bilton, that within limit groups, free groups are.
Yes, yeah, of course, you have this class of
but
groups.
you wrote the Bilton Morales, and, but I think, I thought that Bilton proved that if you have limit groups, then you have a Cephers inside, and therefore
No, so
Or there is
Wilton
something-
considered this class of groups, assuming also hyperbolicity. And Morales just observed that hyperbolicity is not needed. You can assume that it's not needed to put the
Right,
definition
right,
hyperbolicity in the class of X.
Right, but anyway, but as far as I know, it is open question even within limit groups whether profinite completion determines limit groups, determine a limit group itself.
Not free, but any limit group.
Yeah,
Yeah,
so
so
that whether limit group is determined by profinite completion even within this class.
No, I don't think it's no.
And secondly, I think it is very impressive that surface groups are actually determined by profinite completion with the one-relator groups, but maybe you have some generalization of this. I mean, this one-relator groups, you said that it's by simplicity.
Okay, there is it's a class of, it's some subclass of groups of homological dimension 2. We have to put some conditions.
But not all of them, yeah?
No.
I see. Okay, thank you.
More other questions? Tel? Tel? No question? Let me check if he has question in the Zoom. Okay. If not, let's thank again the speaker, the plenary speaker.